We're looking at Sage and Scribe Gas Problems Set 4. This is the key to it. For the first problem, it says using the kinetic molecular definitions only, and you're not allowed to use pressure, volume, moles, or temperature. Describe what is happening to the gas particles inside the bottle as the changes are applied. Looking at this diagram, you'll notice that you have a balloon on top of a bottle, and that balloon that's on top of the bottle is then changed in some way or another, and the applied change is actually temperature. It looks like it's being heated up in a pot. And of course, as a consequence, the balloon is inflating, which means the volume is changing. But we're not allowed to use temperature and volume. We're going to use the KMT definitions for them. So the change is temperature, which is by definition the average kinetic energy or the speed of the particles. So we can say as the speed of the particles increase, the spacing between those gas particles increase as well. Now, I know we're not to mention pressure, volume, temperature, or any of those words, but really the speed is denoted by temperature. So I'm going to put it above it that it's my temperature. And then the spacing between the gas particles is really my volume. So it's temperature and volume being manipulated in this modeling that you see here. Let's go ahead and jump into number 2. It says, what is the volume of the air in a balloon? So we're looking for V2 probably, that occupies, here's my V1, at a temperature T1, and it's lowered to my T2 right here. So let's go ahead and set up this problem. It looks like it's a Charles law problem because there's V and T involved. So I'm going to set up Charles' law. V1 over T1 equals V2 over T2. And 25 degrees Celsius in Kelvin is 298 Kelvin. V2 is my unknown. T2 is 0 degrees Celsius. Adding 273 gives us 273 Kelvin. Cross multiplying, solving for V2 will get me 0.568 liters. We're on to problem number 3. It says calculate the volume, so we're looking for volume given moles at STP. So that means we know the T and the P, because we know STP is when the standard temperature is when it is 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atm. So now because we're at STP conditions, we know molar volume. We know that 1 mole of any gas has 22.4 liters, irrespective of the gas. So we can take the moles and convert that moles into liters immediately. So let's go ahead and use dimensional analysis to convert. So for every 1 mole of that gas, there's 22.4 liters. And straight out, we can get the final answer right away, which is 19.7 liters. Now, we can also use PV equals nRT, because this is actually where we got this equivalence point, or this equivalent statement, is because we use the ideal gas law. So I'm going to show you that you can use the ideal gas law also to solve for this problem. So PV equals nRT is the ideal gas law. So P is in fact 1 atm. That's standard pressure. V is what we're solving for. N is 0.881 moles. R, 0.0821 liters times atm over moles times Kelvin. So now again, for the R, we look to see what the pressure is, and the pressure has to be consistent with the correct R constant, the ideal gas constant. T, which is standard temperature, is 273 Kelvin units. And so when you solve for this, I promise you, you will get 19.7 liters in the end. Now let's move on to number 4. In number 4, you've got your pressure, P1, here's your T1, and your V1. And if it says it's raised to T2 and P2, what is the V2 volume? So it looks like we're using combined gas law to solve, because you're seeing changes in temperature, changes in pressure, and always notice to see if the units are consistent, and they are, kPa, kPa. So you're asked to really find the volume. So V, the changes in volume. So that's why we're using the combined gas law. So let's go ahead and set up the combined gas law. So P1 is 110 kilopascals. V1 is 2 liters. T1 is, in fact, 30 degrees Celsius plus 273, which is 303 Kelvin units. P2 is 440 kPa. V2 is our unknown, so we're going to put V2. And then T2 is 80 degrees plus 273, which is 353 Kelvin units. Once again, you cross multiply and solve for V2, which ends up being 0.583 liters.